Okay, so I did check. I mean, you're never going to know this, but this is the second video I've started, and I just wanted to check and make sure that the audio works, and it does work. Hello. I hope you're well. I am looking at lesson 1-8. You should be able to see that right now on your screens. This is a video for lesson 1-8 for Providence at Home. We are going to look at number systems, and I just want to jump right in. So again, your book can be open to page 45. I will keep this up on the screen though, and we are going to go through, let's see, 6 examples. We'll see, maybe all 6. Excuse me. So let's talk about a number system, 1-8 number system. And what do we want to do right now? We want to understand how different mathematical questions yield, or should we say yield? Let's say necessitate, make necessary, necessitate different number systems. In other words, imagine a caveman. What kind of counting did cavemen do, right? They started with what we would call the counting numbers. And the counting numbers are exactly what they seem like to you. 1, 2, 3, 4, 10, 100, on and on forever, right? And so this is where we start. In the book, they also call this the natural numbers, 1, 2, 3, on and on forever. And there are certain kinds of operations that you can do on the counting numbers that will only ever generate new counting numbers. For example, addition. If you add any two counting numbers, you're only going to get more counting numbers back. So for example, 5 plus 7 generates a new counting number, 12. Multiplication also works this same way. So with the counting numbers, we can add and we can multiply, and it will only ever generate new counting numbers. So if I did something like, say, 2 times 1,000, it would generate the new counting number 2,000. But as soon as I want to do a new kind of mathematical question, remember that's what we're thinking about here, and I want to add on, say, subtraction, well, now the counting numbers don't necessarily help me, because you'll notice there is no counting number 0, so I can't do something like 3 minus 3. So right now, I don't know what the answer to 3 minus 3 is, because that's not in my number system. I definitely don't know what the answer is to a question like, say, 5 minus 27. I really don't understand that if all I have access to are the counting numbers. So as we ask new kinds of questions, we end up having to use new kinds of numbers. And so the next one out, should we do like a rainbow here? Yeah, of course we should. The next one out. Now in the book, they mention whole numbers. I really hate the whole numbers. I think it's a silly category because all it is all the counting numbers. Or again, in the book, they say the natural numbers. All it is all the natural numbers plus 0. So that's really, I think, unnecessary. I just like to skip right out to the integers. So for me, the integers are the next useful group out. And the integers are going to include all the counting numbers, but they're also going to have the answer to questions like 3 minus 3. So now all of a sudden, this isn't a question for us anymore. Now we can actually say, oh, that's 0. And something like 5 minus 27, that's not a question for us anymore. Now we can actually say, oh, that's negative 22. Because the integers are all the natural numbers, 0, and their opposites. So of course, this still includes things like 1, 2, 3, 4, on and on forever toward infinity. But it also includes negative 1, negative 2, negative 3, negative 10, negative 100, and so on. And of course, as I said, it also already includes 0. So the integers, again, if you want to write a definition down somewhere, I guess maybe I'll do that. If you want to write down integers are all the natural numbers their opposites, in the sense of additive inverse opposites, opposite signs, and 0. The one number that is neither positive nor negative. Okay, so now we're good with addition, subtraction, and multiplication. Any two integers you add are only going to give you integers back. Any two integers you multiply are only going to give you integers back. Again, if we want some more examples in here, 3 times negative 4 is going to give you back negative 12, and that's good, right? That's still an integer. We still know how to answer that question. 5 plus negative 3 is positive 2. We only get integers back here. So addition, multiplication, and subtraction, we're good on the integers. But then, of course, we want to ask a question like, well, wait a second, what about, say, 5 divided by 2? Now, how am I supposed to answer that using the integers? I can't, because 2 doesn't go into 5 exactly some number of times. It goes in a little bit less than 2 times, or I'm sorry, that's not right, a little bit less than 3 times, but a little bit more than 2. Or, something like negative 3 divided by 10. How am I supposed to answer this with the integers? I can't. And so once again, I need a new kind of number. And so as we start to introduce division kinds of questions, let's see, Roy G. Biv. Yellow's not going to show up, so let's do a green from here. I need a new kind of system. I need the rational numbers, the rationals. And all of these have some symbols that I'll cover in a little bit. And again, as I'm doing these circles, keep in mind the counting numbers are inside the integers because they belong to the integers. And then the integers themselves are inside the rationals because they belong to the rationals. And so any number that's all the way inside here is going to be both an integer and a rational number, where something out here only in the rational area would be rational, but not be an integer, not be a counting number. So the rationals are exactly what they sound like. They are ratios. And so negative 3 divided by 10, now I can say, oh, that's the ratio. Let's actually go with a darker green. That's the ratio negative 3/10. Or sometimes, of course, we write this in decimal form, negative 0.3. And 5 divided by 2. It's not the case that we can't answer that anymore. Instead, we can now say, oh, that's 2.5. Or the fraction, 5 halves. Or, if we are sadistic for some reason, the terrible mixed number, 2 and 1/2. Any of these would count as rationals. Any other fractions, anything that can be a ratio, 3 over 17, negative 18 over 5, all of these count as rational numbers. So again, just to recap, that's a new mathematical question of division, and that's answered by the rationals. Now, I want to take this whole system and, I do need a definition for rationals, don't I? Okay, I'll give you that definition in just a second. So I'm going to take this whole system, and let's paste it here. Oops. And make it a little smaller so we have more room. And actually, oh, of course. Okay, hold on. Why did you do that? Stop. One more try. Here we go. There we go. That's what I wanted. Make that a little smaller. Okay. Definition of the rationals, which we'll do in our lovely forest green. The rationals are any number, any number that can be stated as the ratio between two integers. The ratio between two integers. And again, that's why we call them rational. The symbols that we need to know so far. So the natural numbers if we're going to do our little color coding again, the naturals are defined by this n with kind of a second bar on it. It ends up looking kind of fancy. That is terrible. It ends up looking, let's just do that, n with a second bar on it. The integers, for a reason I will let you look up and then come on Tuesday and impress me with.
Testing, 1, 2, 3.
Oh goodness, testing,
one,
testing,
two,
testing.
three.
The integers use this special z, and again, I'd like you to come to class and tell me why that is, or email me and tell me why that is. And then the rationals use this special Q symbol, again, a special double Q. So we can do addition, we can do subtraction, we can do multiplication, and we can do division. What other kinds of questions could we possibly ask? When would we ever have questions that could not be answered by the rationals? And that's when we get into the focus of this lesson. So I've had this lesson up the whole time. Square roots and square kinds of questions. So imagine, one more time, let me copy this and move it. So frustrating. There we go. Oh, and that worked that time. I don't know why. Okay. Imagine that we had a question like, say, we know something squared. We'll call it x. We know that x squared.
Testing, testing. Testing, 1, 2. Testing, 1, 2.
Testing, 1, 2. I think it works.
Testing, 1, 2. Testing.
Let's make sure. Let's double check, triple check. Imagine we had a question like x squared, something squared, equals 16. This question we can say what x is, right? It's easy enough to say that x is 4. So we don't need a new kind of number for that question. But there's no particular reason x squared has to be 16. Imagine that x squared was 20 instead. Now we don't really know what x is. We couldn't say that it's 4 because we just said that 4 squared was 16. We couldn't say that it's 5 because 5 squared is 25. That's too big. So x is some number that lies between 4 and 5. Now you might guess, well, if it's between 4 and 5, is it 4.5, right? Is it that x is actually 4.5? But as you multiply 4.5 times 4.5, unsurprisingly, you're not going to end up getting exactly 20, although we do actually get quite close. Let's see, 4 times 5 again is 20, carry the 2, 18. And then we end up with 20.25. So it's just a little bit too large. So then you might say, okay, so it's not 4.5, but could it be 4.4 instead? And so you multiply 4.4 times 4.4, and you're going to end up getting 19.36. You can check my math on that later, but I'm reasonably sure that's what we're going to end up with. And so you say, okay, well, maybe it's not 4.4, but maybe it's 4.45. And hopefully you're getting a sense already, well, that's not going to work, because when we multiply the 4.45, it's going to end in 5, right? The 5 times 5 is 25, and no matter what else happens over here, when we add everything up, we're going to have a 5 at the end. But we're not, oh goodness, quadruple check. What a day. Okay. We're not going to have a 5 at the end. This answer was supposed to be 20, right? We're looking for something that ends in a 0 or a 0.000. Well, what's going on here is that the rational numbers don't end up helping us answer this question. We need a totally new kind of number. So this is the first one that is actually totally separate from the rationals. We need something called the irrationals, not irrationals. The irrationals are any number, any number that cannot be written as the ratio between two integers. Integers be written as the ratio. Should we move that? I guess so. Oh, took the circle with us. any number that cannot be written as the ratio between two integers. So these would be things like the square root of 20, which perhaps you can tell is what the actual answer for x would be, or the square root of 22, or the square root of 112, or testing, 1, 2, let's make sure, and quintuple check it today, perfect. Oh, hextuple check it. The negative square root of 24 would work here. Anything that's basically not a perfect square. And of course, you may be aware there are other kinds of irrational numbers, like pi is an example of an irrational number. 3.141592653589793238462 and so on and so on and so on. It's going to go on forever and it's never going to repeat. So that's one thing I did not mention about the rationals over here. The rationals, anytime we write them as a decimal, are always going to either end or eventually they will repeat. The irrationals don't work that way. 0.00100100001000001. That's not actually repeating. There's a pattern there, but you'll note no particular set of digits ever repeats. Whereas the rationals are going to be things like 0. Let's make sure to put it in our circle. 0.343434, on and on forever. That is going to have to be rational. So the way we expand these as decimals also ends up telling us whether they are rational numbers or irrational numbers. In this lesson, we mainly want to talk about the square roots for the irrational numbers, but I just want you to be aware there are lots of them. And finally, let's say this whole thing is together what we call, so we're going to box the whole thing, this is all the real number system. There are other kinds of numbers even beyond these, but as far as the kinds of questions we're going to be asking in Algebra 1, so you can also think of this as the kinds of questions people asked up until about the 15th century, the real number system is all we need. We don't need anything outside of this real number system until we get to, again, about the 15th century. And then we start to need non-real numbers, imaginary numbers. Later on, we get into surreal numbers and all kinds of crazy stuff. But we're not going to worry about that right now. We are going to finally jump into some examples. Let's talk about how to do something like example 1. So example 1 has us simply classifying these numbers. So something like 5 over 22, we're trying to figure out, which circle does 5 over 22 fit into? And you can probably tell, well, it's not a counting number, right? We don't count in 5/22. And it's not an integer because it's not the opposite of a counting number and it's not 0. But it is the result of division. And so this one we would simply say is rational. Or if we were using our special symbol, we would give it the Q with the double bar. Something like the square root of 81. Now you might think, oh, square root, so automatically that's going to be irrational, right? But no, not so fast, because what I want to do is make sure I understand the value of my number first. The square root of 81 looks like an irrational number, but clearly we can evaluate this. This is just equal to 9, right? And so then we ask ourselves, well, what does 9 belong to? 9 belongs to the naturals. 9 belongs to the integers. 9 belongs to the rationals. So remember, if I'm in that innermost circle, then I also have to be in the outermost circles. Irrationals would not count because irrationals are totally different from the rationals. Remember, the irrationals were over here on this other side, and so they are separate from these other groups. But these groups that are in the same circles as each other, we want to make sure we list them all. If we're doing it in symbols, our special N, maybe I should do a different one. There we go, that looks better. Special N, special Z, and special Q. For C, what are we looking at on C? The square root of 56. Okay, so again, you might be anticipating, well, now hold on a second. A moment ago, a square root ended up being a natural number, so is the same thing happening here? And you just have to know, well, is 56 a perfect square? And of course the answer is no. In the book they say, well, it's about 7.48331477 ... which does not repeat and also never terminates. And so we actually can't say what it's equal to. We can only say, well, it's about 7.483314, blah, 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 on and on forever. And so this one would be irrational. Now, there's not really a symbol for the irrational numbers, although sometimes we do use a weird symbol, R minus Q. In other words, the irrational numbers, let's go ahead and define this so that this makes sense to you guys, are all the real numbers, that's what the special R is, the real numbers, except the rationals. In other words, the irrational numbers are all the kinds of numbers that are real but are not rational. And so that's the symbol we use for that irrational group sometimes. Take a moment on your own. You can pause this video, work out Check Your Progress 1A and 1B. You have 5 seconds to pause the video. 5, 4, 3, 2, 1. Okay, you should have paused and then unpaused. You're back now. You've got an answer. Check Your Progress 1A. Let's take a quick look at that one. Check Your Progress 1A. We've got 6/11, which you should be able to tell, oh, that's division, so this is rational, right? So we're going to give that the special Q. And then Check Your Progress 1B, the negative square root of 9.16. I'm reasonably sure if we go to the calculator, it's going to give us some kind of weird 3.04-ish, maybe, 3.02-ish. I'm going to say ish because it's just going to go on and on forever, and it's not ever going to repeat, definitely not ever going to finish, and so that is irrational. And if we want to give it the symbol, special R minus special Q. So that's what you should have done for Check Your Progress 1A and 1B. Let's move on to example 2. This time we want to graph the numbers on a number line. So something like A, we've got the numbers -4/3, -1/3, 2/3, and 5/3. And I could make quick decimal approximations of all of these numbers, but in this case, since they're all thirds, I'm actually just going to draw my number line in a way that makes it easy to get these onto the number line. So I'm going to have this be 0 on my number line, and then I'm just going to label, going down, -1/3, -2/3. I say going down, but really I mean moving to the left, right? -3/3, of course, is the same as -1, and then -4/3. And in the same way, as I count up, I get +1/3. And when I say up, again, I really mean to the right, 2/3, +1, 4/3, and 5/3. As far as graphing this, all we need to end up doing is putting dots on the numbers that we see. So -4/3 was one of them. -1/3 was another. 2/3 was another. And then there it is, 5/3. Now, it's not always going to be so nice where we get all thirds, but in this case it was, so that's simple enough to do. I don't think I want to do examples B or C yet. We're not going to be graphing things like that just yet, so let's skip B and C. You can also skip Check Your Progress to, oh, it's
Testing 1, 2, 3.
seventh check.
Testing 1,
Seventh
2,
check.
3.
Wow.
Testing 1, 2, 3.
What an experience you all are having to be present for the 7th check of the day. Lucky you. Go ahead and take a look at Check Your Progress 2B on your own. So I'm going to turn that into a B. Actually, I'm not quite sure. Well, I wouldn't want to do B. I would want to do A, but I'm really not sure what they mean by the ... here. I guess what we could say is if we're looking at the set -5, -4, -3, -2, ... So on a number line, if this is 0, and let's actually just kind of do every other one going up and down. So that's -2, that's -4, that's -6, that's +2, that would be +4, and so on. we start with a solid dot on -5. We don't want to keep shading in the whole number line because nothing between -5 and -4 worked. It's just that -4 is next, and then -3, and then -2, and -1, and 0, and so on. And so what we want to make sure we're doing is not shading in the whole number line. That's what we do sometimes with inequalities. That's what you would do on Check Your Progress 2B, and that's what you would have done on example 2B and 2C, as you can see in the book. Instead, we just want to make sure we are plugging in only single points if it's not an inequality. And so that is the point there for example 2 and Check Your Progress number 2. All right, still going. Let's talk about square roots. So imagine something, and the book does the square root of 64. When we use the square root symbol, typically what we mean is there is some blank times blank such that these two are the same, and that's what we call the square root of 64, right? So for the square root of 64, since we know that 64 itself is 8 times 8, we would usually say, okay, so the square root of 64 is 8, right? But if you think about it, there's another number that when you multiply it by itself also gives you back 64. We can think of another blank times blank that makes 64. Take a moment, think about it. What else times itself gives you back 64? Ah, yes. -8 times -8 gives you back 64. Well, what's going on here, right? Is the square root of 64 supposed to be 8? Or is it supposed to be -8? Or is it in some sense both? And so this is where we get into something we call the principal value of a square root. You can see in the book the principal square root. Sorry, not radical sign. The principal square root. What we mean when we say principal square root is that although it is true that -8 times itself gives us back 64, that's not usually what we mean when we ask about a square root. If we wanted the negative square root, we would have to specify. And so here's the way you do that. If I just see square root of 64, we want the principal value, which is +8. If I wanted someone to tell me the answer of -8 specifically, I would need to specify, oh, I want the negative square root of 64. And finally, if for some reason I actually did want both positive and -8, I would have to use what we call the plus or minus sign. And plus or minus square root of 64 is what gives us back plus or minus 8. All of which to say on example 3, when they ask us to find the negative square root of 49 over 256, I know, oh, they specifically want a negative value back. So I'm going to put my negative sign right away. And then I'm going to think to myself, can I take the square root of this fraction? Which really ends up meaning, can I take the square root of the numerator and the denominator separate from each other? So the square root of 49 is 7. The square root of 256 is 16. And that would end up being the value that I'm interested in. Let's actually do the Check Your Progress number 3 together really quick, because I know this is kind of a weird concept. So A has another strange looking square root, 4 over 121. This time, though, I notice no sign in front of the square root. And so I realize, oh, they just want the principal value, which is going to be positive. We could write a plus sign, but normally when things are positive, we just don't put any sign at all. And then we take our square roots, right? For the numerator, the square root of 4 is 2. For the denominator, the square root of 121 is 11. And so there it is. The principal value of square root 4 over 121 is 2 over 11. Or on part B, they specify, okay, we want the positive or negative square root of this number 1.69. And so right away, I know that as I write down my answer, I'm going to put a plus or minus sign. Now this one unfortunately is not a fraction, but if you're familiar with your square roots, you know that 13 squared is 169. And so what that must mean is that 1.3 squared, when we multiply it, that would be 2 decimal places, right, becomes 1.69. And so using your calculator or using what I just showed you, we could say, oh, okay, so that is the positive or negative, that is positive or negative 1.3. I am going to skip example 4. I trust that you can plug those numbers in and look at that yourself. There's a formula there that you can use if need be. And what I want to finish up with, let's knock out page, what is this, page 48. Let's do example 5 and example 6. So on example 5, we want to say between two real numbers, which one is larger? And there are a few different ways we could end up doing this. I think the easiest way is to approximate both of the numbers as decimals and then just contrast and compare. So for example, square root of 19. Well, I know that the square root of 19, whoops, gave it away a little bit. I know that the square root of 19 is greater than the square root of 16, right? And the square root of 16, of course, is 4. And I know that 4 would be greater than 3.8 repeating. So even if I don't know exactly what the square root of 19 is, I would need to go to the calculator, and it would end up being like 4.38-ish, I think. But even if I don't know that, I know it's bigger than 4, and so I also know that it has to end up being bigger than 3.8 repeating. Let's try the same thing on example 5b. So for 5b, I'm comparing 7.2 repeating to the square root of 52. And again, what I notice here is, well, the square root of 52 is something that the square root of 49 would be less than. And I know what the square root of 49 is. It's 7. Oh, sorry, actually, this doesn't end up helping me in this case. So I know that the square root of 52 is something a little bigger than 7. I think I'd have to go to the calculator, though, because these look like they're going to end up being pretty close to me. Like 7.2 times 7.2, if I was just trying to compare that directly. This is going to end up being, what is that, 4, 14, 0, 14, carry a 1, 50. So this one ends up being 51.84. And again, that's really close to 52. And so I think without a calculator, this one is just not really a great one for us to compare. So we would have to go to the calculator. Let's do that now. And let's find out square root 52. There it is, 7.2111, on and on forever. Well, not forever, but without repeating. But remember, this one was 7.2 repeating, which is going to be 7.2222, on and on forever. You can see 65 over 9, which ends up being the same thing as 7 2/9. So they're very close, but what this ends up meaning is that the 7.2 repeating must be a little bit bigger. And again, it was really the calculator that helped us do that there. So some of these you are going to need to use the calculator on for the homework. I will let you try that out for Check Your Progress 5A and 5B on your own. So go ahead and pause the video. 5, 4, 3, 2, 1, pause. And we're back. You've had enough time to pause. So let me quickly give you the answers. 2 2/3. This is Check Your Progress 5A. 2 2/3. 2 2/3 is the same thing as 2.6 repeating. The square root of 5, on the other hand, is something like 2.2-ish. And so it should be pretty clear in this case that 2 2/3 is greater there. And then for Check Your Progress 5B, 0.8 repeating compared to 8/9. You don't have a good reason to believe this yet, but you're just going to have to trust me. 0.8 repeating is the same as the fraction 8/9. So a little bit of a trick question there. These end up being equal to each other. All right, goodness. Last but not least, thank you for sticking with me. Last but not least, example 6. Man, it's going to be quite a time of it, turning this one into a 10-minute math minute video. We've got 2.63 repeating, negative square root of 7, 8/3, and 53 over negative 20. And we're supposed to arrange these from least to greatest. Well, the first thing I would do is I would say, well, these two are negative, so they're going to have to be on the left. And then these two are positive, so they're going to have to be on the right. So let's start rearranging there. Negative root 7 and negative 53 over 20. And then 2.63 repeating. And then 8/3. Now, I don't know, which one these go in. I'm not sure about yet. Which order these go in, I'm not sure about yet. But at least we have the lower two and the upper two. At this point, I would say go to the calculator so we can get the square root of 7. So let's clear that out. Square root of 7. 2.646 if we round up. 2.646. And then, so negative 2.646. Whereas negative 53 over 20, negative 2.65. Oh, gosh, they are being mean. These are so close. Remember, as we move further to the left on the number line, the numbers themselves look bigger, right? And so, in fact, the negative 2.65 is going to be to the left of negative 2.646, on and on. And then the same thing ends up being true over here with the positive numbers. 8/3 is the same as 2 and 2/3, so that's going to be 2.66 repeating. So it goes 2.63 repeating, and then 2.66 repeating. And again, you can go into the calculator to get all of this. And so finally, I would just say, well, let's make sure we've got the right numbers matched up as we go. Remember, negative root 7 was this one over here. 8/3 was this one over here. And so my final order here would be negative 53 over 20, comma, let's put this in blue. Negative 53 over 20, that's what the 2.65 was, that's where it came from. Negative root 7, that's where that one came from. 2.63 repeating, of course, has been the same from the very beginning. And then this was the 8/3. And so that is the proper order from least to greatest. I will let you use your calculator and figure out Check Your Progress 6A and 6B on your own. You can come back to class and ask me if you got those right with your notebook, or take a picture of your notebook, send it to me over the Google Classroom. However you want to do it would be fine with me. That is your lesson 1-8 on the real number system. I hope that was helpful. If you have questions, write them down. Be sure to get those back to me. And yes, have a great weekend.